Hey guys, welcome to another session on maths for data sciences. So from last 2-3 sessions, we have been looking at different metrics that could be derived for a continuous distribution, and we specifically did it for an exponential distribution. So in our very last session, we looked at how we can derive some metrics that defines the shape of the distribution. Specifically, we looked at skewness of the distribution and kurtoses of the distribution. And we saw that for exponential distribution, it is a positive skewed distribution since there's a right tail, it's a right-sided tail distribution, and therefore it has positive skewness, and the value was calculated to be 2 in this case. Similarly, for kurtoses, which gives the relative strength or relative size of the tails and peakedness of the distribution, we saw that it's a leptokurtic distribution which had an excess kurtosis value of 6 because it had a kurtosis value of 9, and to get the excess kurtosis, we subtract the value 3 from the kurtosis. 3 is the mesokurtic distribution kurtosis value, which is for a normal distribution. We subtract 3 from total kurtosis to get the excess kurtosis. And we saw that for leptokurtic distribution specifically, they have heavy tails and sharp peak, and therefore exponential distribution, that is true that we had heavy tails and sharp peak for exponential distribution. So these two metrics were specifically designed to get the sense of shape of a continuous distribution. Next, we'll be looking at our third continuous distribution. So we have looked at continuous uniform distribution, exponential distribution, and now we would be looking at a normal distribution. So for normal distribution, we would not be really deriving a lot of metrics like we did for exponential distribution. The reason being that the PDF for a normal distribution is a little complex, and therefore the integral as well becomes a little complex, and therefore we will not be going into derivations, but we'll still be mentioning all the metrics that could be defined for a normal distribution. Now first let's define a random variable. So let us say x is a random variable which is normally distributed. Now we had in an exponential distribution, if you guys remember, we had only one parameter. So in exponential distribution we had one parameter, which was lambda, which was the mean rate of arrival. But in case of normal distribution, it is defined by two parameters, which is mean and the standard deviation. So these are the two parameters which are normally used to define a normal distribution, and the parameters are nothing but mean and standard deviation of the distribution itself. So for exponential distribution, we saw that mean is equal to 1 upon lambda, and standard deviation was equal to 1 upon lambda as well, because the variance was 1 upon lambda square. Therefore standard deviation was 1 upon lambda as well. But in case of normal distribution, the two are not equal, and it could be equal, but they could be different as well. And the values of the mean and standard deviation of the distribution actually defines that particular normal distribution. Now we'll be looking at some of the properties of normal distribution one by one. So the first property is that has a bell-shaped. It's a bell-shaped distribution, as we can see from the PDF probability density curve given here. So this is the PDF probability density curve shape, and we can say it has a bell-shaped curve, or it has a bell-shaped distribution here. Next, it is symmetric about the mean value, and therefore what could it be called? It could be called to have the zero skewness. Since skewness is a measure of asymmetry for the distribution, and we can see that normal distribution has a perfect symmetry about its center, therefore it has zero skewness. And this is also the reason that all the three measures of central tendency, which are mean, median and mode, are equal to each other. So mode is nothing but which is the value of x at which the peak of the distribution is obtained, which is clearly here at the center as well, and therefore the mean, median and mode are equal for a normal distribution. Next, we can see that it's a unimodal distribution. So exponential distribution was also unimodal. So if you remember, exponential distribution had a shape something like this, and the mode here was equal to 0. Now here also there is only one mode, which is this particular value, and therefore it's a unimodal distribution since there is one mode value. But then what is bimodal distribution? So bimodal distribution could have shapes something like this, where there are more than 2x values at which the maximum value of the PDF could be achieved. So this is an example of a bimodal distribution. But normal distribution is a unimodal distribution. Next, we will look at a term asymptotic. So the tails never touch the x-axis. So if you can see, when I am drawing the PDF here, you will see that the tails are not exactly joining the x-axis, but they go infinitely in both directions. So they tend to have value equal to 0, which means touching x-axis, but they never have the value of x equal to 0. And this particular property is called the asymptotic property for the normal distribution. Next, the PDF of the distribution. So the PDF itself for the distribution. So just like in exponential distribution, we had the PDF as fx equal to lambda e to the power minus lambda x. But in case of normal distribution, the PDF is given as 1 upon root 2 pi sigma. So sigma is not under root, multiplied by exponential x minus mu whole square upon sigma square. So this is how we define the PDF of a, oh, there's a 2 here as well. This is how we define the PDF of a normal distribution. And one can see here that if we put, let us say, x equal to mu. Now once again, like we defined the mode of the exponential distribution, if we have to maximize this PDF value, we will have to make this equal to 1, which means the power of exponent should be equal to 0, and therefore x should be equal to mu. And this is the reason that mode of the distribution is equal to the mean of the distribution, which is equal to the mu value for a normal distribution. Next, we saw one of the metric skewness here, which has a value of 0, but then there is another metric, which is the kurtosis, and this is equal to 3, so that the excess kurtosis for a normal distribution is equal to 0, and therefore this is called a mesokurtic distribution. So we saw in the previous session that the distribution with 0 excess kurtosis is called a mesokurtic distribution. So these are some of the properties of normal distribution, which defines the PDF and shape and the measures of central tendency for the normal distribution. Now next, we would be looking at how we can calculate the probabilities for a normal distribution. So in case of exponential distributions, we were able to calculate the probability by using the integral. So for example, let us say we are calculating probabilities. So probability under any PDF is actually defined using the integral between x1 to x2, and we simply integrate the PDF in the given range. But in this case, since I previously mentioned that the integral of this complex PDF could be difficult to achieve, so what we use is, for normal distribution, we normalize the values into their z-scores and then compute the probabilities. So to compute the probabilities, between any two x values for a normal distribution, we will have to first convert it to their z-scores, which we'll be now looking into more detail. So let us say we are given normal distribution which has a mean of 50 and a standard deviation of 5. Now we are asked to calculate the probability of x lying in the range 45 to 60. So how do we do that? This is nothing but, so first, as we saw here, we first convert them to z-scores. Now how we do that? Z-score is defined as x minus mu upon sigma. So x is nothing but the x value for which the probability is being calculated. So this can be written now as 45 minus, the mean is 50, the standard deviation is 5, and z. So we are converting x to z, so therefore I have replaced x with z here, and we have again 60 minus 50 upon 5. This is given as p minus 1 z2. Now this can be calculated as p z less than 2 minus p z less than minus 1. Now the notation for this particular expression, whenever we have, let us say, this kind of an expression here, p z less than z, this can be written as this particular expression. So we can write this here as 2 minus 1. And another thing to note here, now that we have converted them to their respective z values, we can use the z distribution to calculate the probabilities, and z distribution has a mean value of 0 and a standard deviation value of 1. So one has to remember, this is called a standard normal distribution. So this is called the standard normal distribution, which is nothing. It is also a normal distribution, but with mean always equal to 0 and standard deviation always equal to 1. Now for standard normal distribution, we can use standard normal tables to obtain the probabilities. The standard normal table is given on the left hand side here. So now let us try to calculate the probabilities. We have to calculate the probability for z equal to 2. So in this particular step, z equal to 2 and z equal to minus 1. Now for z equal to 2, we can see this particular row, which is showing the value for z equal to 2 as 0.9772. So we look at the first column because we are looking at 2.0. And the value, this particular table gives the value for pz less than z, and therefore we get pz less than 2 as 0.9772. So we get from the table above pz less than 2, which is 2 as 0.9772. Now for pz less than minus 1, so one has to again do some other computations here to get that particular value. So I'll just shift this one here. Okay, so now we have to next calculate p z less than minus 1. Let us quickly draw a rough graph here. So let us say this is a normal distribution. Let us say this is a standard normal distribution. So this is a standard normal distribution with mean equal to 0 and standard deviation equal to 1. And since we have to calculate z less than minus 1, it would be this particular area. So area under the PDF represents the probability for that PDF in the given z range. Now since this is z less than minus 1, now the thing here is we know that the normal distribution is symmetric about the center, and the center of the distribution here is z equal to 0, since the mean of the distribution is 0. Therefore p z less than minus z is same as p z greater than z, which is, if we take this as 1 and let us say, so this is minus 1 and this is 1, then the shaded region on the left hand side should be equal to the shaded region on the right hand side, which means pz less than -1 should be equal to pz greater than 1 because of symmetry about z equal to 0. Now this can be calculated as 1 minus pz less than 1 using complement rule of probability, because we know that pz greater than 1 plus pz less than 1 have to be equal to 1, since these are the only two possibilities. Therefore pz greater than 1 can be calculated as 1 minus pz less than 1, and this can be calculated now as 1 minus phi 1, and this now can be easily seen from the standard normal tables from this particular row here, which is 0.8413. so this particular value, and earlier we used this particular value 0.9772. so now writing 0.8413, and this comes out to be 0.1587. so this is the value of pz less than -1. Now to get our initial probability, we can simply put these values. So we had to calculate phi 2 minus phi -1. This is nothing but 0.9772 minus 0.1587. So now one can just simply subtract them to get the required probability. So this is how we use the standard normal tables to get any probability in any x range for any normal distribution. So the first step is always to convert the normal distribution into their z-scores or into a standard normal distribution which has a mean of 0 and standard deviation of 1. And the next step is simply to use the standard normal tables to get the required probability. Okay, so next we would be looking at a simple rule for normal distribution. It is called the empirical rule of normal distribution. What this states is 68% of the values lies within one standard deviation of the mean. This simply means P mu minus sigma less than x mu plus sigma is equal to 0.68. Again, this can always be checked using standard normal tables again. So basically this x probability could be converted into z probability p minus 1 z 1, because because mu minus sigma minus mu upon sigma will give -1, and mu plus sigma minus sigma upon mu plus sigma minus mu upon sigma will give 1, and therefore we are left with this particular value. And we already know pz less than 1 was 0.8413 like we saw in the previous case, and pz less than -1 is 0.1587. so one can see that it is approximately equal to 0.68. Similarly, the empirical rule of normal distribution also states that 95% of the values lies within 2 standard deviation of the mean, and similarly 99.7% of the values lies within 3 standard deviation of the mean. So these are the 3 rules which one can remember, because they can quickly be used to get the probabilities for normal distribution. So this is how we calculate the probabilities for normal distribution in general. So this is it. This was an introduction for normal distribution. We looked at various properties with respect to shape of the normal distribution. We also looked at the PDF of a normal distribution. So this is the PDF here, which is given as 1 upon root 2 pi sigma exponent of minus x minus mu whole square divided by 2 sigma square. Then to calculate the probabilities, we looked at how we first need to convert them into z-scores, and then using the standard normal tables for the standard normal distribution, which is the z distribution here, we can calculate the required probabilities. And finally, we looked at the empirical rule of normal distribution, where we saw that 68% of the values should lie within one standard deviation of the mean, 95% of the values within two standard deviation of the mean, and 99.7% of the values should lie within three standard deviations of the mean. This is an introduction to the normal distribution.